Hello again, physics friends. Today we're going to talk about a step-by-step approach to the Lagrangian mechanics formalism. And this is much more of a how-to rather than a derivation. This is meant to give you a set of tools to actually solve problems and a process to follow to do so. So I think of this as a 5-step plan, and here are the 5 steps that I think about. First of all, choose an inertial coordinate system. When you write down the coordinates of an object in your system, you must reference those coordinates to an inertial frame. In other words, pick an origin that is not accelerating. Okay, and typically we're going to choose an origin that's at rest, that defines a rest frame. Okay, and then once you've done that, you have to then pick one coordinate per degree of freedom in the system. In other words, if there's a way that the system can move independently from other motion, then there needs to be an associated coordinate for that direction. We'll talk more about that in detail and show some practical examples. The second point is once you've identified a coordinate system and selected your coordinates, then it's time to write down the kinetic and the potential energies, and we'll talk through a foolproof way to do that. The most foolproof way that I'm aware of is to write everything in terms of Cartesian coordinates and then convert the Cartesian coordinates into the generalized coordinates, and we'll do an example of that. Step 3 then is just a very straightforward step. It's construct the Lagrangian. You've already found t and you've already found u, and now just take their difference, and that defines the Lagrangian. Your Lagrangian will then be in terms of the generalized coordinates q1 through qn and their time derivatives, the velocities, the generalized velocities, and occasionally you'll deal with a Lagrangian that has explicit time dependence. Step 4, once you have the Lagrangian, is to compute the partial derivatives. In particular, you're going to compute the partial with respect to each coordinate and the partial with respect to each generalized velocity. So you'll have 2 partials for each coordinate qi. The final step is to stitch those partials together into the Euler-Lagrange equations of motion. And there you're going to have to take one additional time derivative of a partial, and then you equate it to the other partial. So just to review, there's one Lagrangian for the entire system. Out of that Lagrangian, however, you will get an equation of motion, a so-called Euler-Lagrange equation of motion for each coordinate. So if you have a system with 3 coordinates, you're going to have one Lagrangian and 3 equations of motion. So I want to take a few minutes to talk through different aspects of the steps. And I'll start with step 1. How do we make sure to choose an inertial coordinate system? And number 2, how do we identify the relevant degrees of freedom that are available to us? Okay, so let's consider the following problem when we're talking about inertial coordinate systems. Let's assume we have a ceiling. Attached to the ceiling is a string with a mass on the end. We have a pendulum, and this is a plane pendulum. It's oscillating in the plane of the page. We could write down the coordinates of this pendulum relative to the point of attachment, and that would be fine because this point of attachment is not accelerating. If we put our origin at that purple point, that is an inertial coordinate system, and we can write down the x and the y coordinates of this bob and talk about the velocity of the bob relative to that origin, and that would be fine because it's an inertial coordinate system. But consider what happens if you take that pendulum and instead of attaching it to the ceiling of a building, say, attach it to the ceiling of an elevator, and then let that elevator accelerate upward. Okay, so now we have something like the following. We have an angle phi, a pendulum of length d, but we've put this in an elevator, and the elevator itself is accelerating upwards. Okay. If you chose that point of attachment, once again, as a coordinate system's origin, you would have a problem, okay? The problem is that if you write the x and y coordinates of this bob relative to that point of attachment, that is a non-inertial coordinate system, okay? So what you want to do instead is choose an inertial frame, perhaps that's the ground or the earth, and put your origin there. So we can't do this. We can't put our origin there, but we could put our origin down here, maybe directly below that point of attachment, but on the ground. That is an inertial coordinate system, an inertial origin. Then we could write the y-coordinate of our bob and the x-coordinate of our bob in that coordinate system. And we would be using then inertial coordinates. So once you identified that inertial coordinate system, now you have to choose a set of coordinates to use. And I think it's worthwhile spelling out how to do that and how to know how many degrees of freedom or generalized coordinates you need. Okay. So let's start with the idea that a point particle could move in general in three-dimensional space. And so for every point particle, we need three coordinates. A point particle, if unconstrained, has three degrees of freedom. And we can abbreviate that DOF, degrees of freedom. Okay. So point particle can translate in, say, X, Y, and Z in 3 dimensions. So we need three coordinates to describe that motion in general. If you have n point particles, then you're going to have 3 times n degrees of freedom, 3 degrees of freedom for each point particle, like so. But we'll typically work in situations where a particle has a constraint, and the constraints reduce the numbers of degrees of freedom. So let's look at a few examples. Okay, our first example of constraints and how to talk about them and how to determine degrees of freedom in a system. We'll just say, let's confine a particle to a plane. Okay, so we might have a box that slides on a table. So we'll have our table like this, and then on it we're going to put a box like so. Okay, and that box can move forward, backward, and left, right on the table, but it can't move up, down, perpendicular to the table. So there's one constraint here. The constraint, we would say, is that if we define a coordinate system that looks something like this, x, y, and then z perpendicular to the table, our constraint would be that z equals 0 or is a constant, which tells us z dot and z double dot are both 0. The particle is not moving in the vertical direction. And so what that tells us then is we start with one particle, and that particle is moving in 3D in general, but we have one constraint, which gives us 2 degrees of freedom. So we'll need 2 coordinates, 2 generalized coordinates. I'll call them Q1 and Q2. And in this case, we could use X and Y to describe the motion in that plane, or we could use R and phi like 2D polar. Okay, but we only need 2 coordinates for this motion. For the next example, let's come back to this plane pendulum. So we have a pendulum, and it's confined to oscillate back and forth in the plane of the page. So what do we have in that case? Well, let's throw on a coordinate system here so that we can talk concretely about this. So we have x, y, and then we'll have z out of the page. Okay, and in that case, we have one particle here, but we have some constraints. So what are the constraints? We have 2. The first is the particle is confined to a plane. Z is 0. Constraint number 2 is that the pendulum bob is always a fixed distance from the point of attachment. We can call it R, the length of the rope, and if we put our origin at the point of attachment of the pendulum, then we have a mathematical constraint, which is the distance squared is constant from the mass to the point of attachment. So x squared plus y squared is a way to express the distance of the point here, to the origin, and that is always going to be equal to the square of that length r. So in this case, we have one particle, so that's in general 3D, but we have two constraints, okay, and therefore we have 1 degree of freedom. And we need a coordinate for that 1 degree of freedom. And what we typically use is the angle of the pendulum from vertical as our generalized coordinate. As a final example, let's consider 2-point particles connected by a rigid rod on a tabletop. So this could be a top view of a table. We have 2-point particles. They're connected by a rigid rod. And so we want to talk about the motion of these particles. So here, I'll lay down again a coordinate system. We could use x and y like that, just as a way to talk concretely. In this case, z would be out of the page. And what do we have in this case? We have some constraints, right? What constraints do we have? Let me give some names to these, like 1 and 2. Okay, so some of our constraints. Number 1, the z-coordinate of particle 1 is 0. Particle 1's on the table. Same for particle 2. Particle 2 must be on the table. There's one more constraint, though, and that other constraint is that the distance between these particles is always constant. And if I might just annotate this diagram, I'll say r is that separation. So the rod has length r. So we can write down an equation that relates x1 and x2 and y1 and y2. And this equation says that the separation between these two particles is always fixed at r, even if the whole system rotates or translates. So this is interesting then, because we have two particles. So that would be 6 degrees of freedom, 6-dimensional motion in general, 3 for mass 1 and 3 for mass 2. But we have also 3 constraints. So that leaves us with 3 degrees of freedom. What are these degrees of freedom? Well, the rod can translate up and down or left and right. That's 2 degrees of freedom. And then the rod could rotate, and that's the 3rd degree of freedom. Okay, so we need 3 generalized coordinates to describe this motion: Q1, Q2, and Q3. And here it's convenient, very convenient, to think about the center of mass of the system and the position of the center of mass of the system. So Q1 and Q2 could be the x and y coordinates of the center of mass. Okay. And then the 3rd coordinate could be this angle of the dumbbell relative to some reference position. So we have translation given by the x and y coordinate, and we have rotation given by the 3rd coordinate, for a total of 3 degrees of freedom. Even though we have 2 particles, which in general would require 6 coordinates to describe, here we have 3 constraints, so we only need 6 minus 3, or 3 generalized coordinates. So I do want to say a few words about the second step here, about finding the kinetic and potential energy, writing those down in terms of these generalized coordinates. Sometimes the problem naturally lends itself to a particular coordinate system, right? So if you talk about a plane pendulum or a spherical pendulum, in that case, you are kind of naturally suited to use spherical coordinates or plane polar coordinates. But there's often going to be problems where you're neither here nor there on a particular coordinate system, and you need to kind of use some generalization or a mixture of spherical coordinates and Cartesian coordinates and so on. So I just wanted to talk through a foolproof technique for writing down kinetic and potential energy for a problem. And the basic outline is, number one, start by writing the coordinates as Cartesian, and then number two, convert from Cartesian to the parameters of interest, the coordinates of interest. So let's talk about this in the context of a specific problem. So imagine the following. We're looking down from above on a thin wire that's bent into a circle. On that wire, we put a bead. And in general, like if nothing else was happening, the bead would be free to move without friction on this hoop. Okay, so if you flick the bead, it would move around this hoop and just continue to move, right? In this case, gravity is pointing into the page. And so if given a little kick, the particle would, or the bead would just move around the hoop without stopping, no loss of energy. In this problem, however, we're going to pivot the hoop at one point, point A, and we're going to say that point doesn't move. It's attached to the table, maybe pinned to the table, but the whole hoop can rotate around point A. So if you'd like, we can think about the whole hoop as rotating at angular speed omega, and we're going to actually drive this. So no matter what the bead is doing, the hoop is going to be rotating around point A at an angular frequency omega. Okay? And our goal is then to study the motion of this bead. And we want to know a couple things, like number one, how many degrees of freedom are there? How many generalized coordinates do we need? And what would be a convenient generalized coordinate to use? Okay, so here's how we can think about that. So let's think first about constraints, okay? So we have one particle of interest, and it is, in principle, could move in 3D, but it's experiencing some constraints. What are some of the constraints? The first is that it's confined to this plane, right? So if we think about x pointing to the right and y pointing up on the page and z going out of the page, then this particle is subject to the constraint z equals 0. So it's no longer a 3D problem, it's a 2D problem. But there's an additional constraint, right? Because this particle is on a hoop, it can't move anywhere in the plane that it wants to. It's confined to moving along this hoop. And so if we think about the middle of the hoop as this blue point here, we know that wherever that blue point is, that blue point is going to move in a circle around point A, but wherever that blue point is, we know the bead will always be a fixed distance away. Okay, so if we said that we think about like the radius of the hoop, we can call that r, we can say that the bead is always a distance r from the center of the hoop. Okay, so we have one particle that in principle could move in 3D, but we have two constraints, and so we have only 1 degree of freedom. And if there's 1 degree of freedom, we just need one generalized coordinate. So what coordinate should we use? Well, since the bead is confined to move around the hoop, a coordinate around the hoop would be sensible, okay? And there's more than one choice. For example, you could talk about some linear coordinate, I don't know, we might call it s, where s equals 0 would be at point B, and then you would measure a distance around the hoop relative to B, or we could talk about an angle phi between where the bead is and the line, the diameter from the fixed point of the hoop to the opposite side of the hoop. I'm going to go with that second choice. We'll use the angle phi as a measure of the position of the bead on the hoop. Now you might ask, well, isn't the hoop moving? Yes, it is moving. It's being driven to move in a rotational way at a fixed angular speed omega. Because that angular speed is fixed, it's not a degree of freedom, it's just a motion, right? And so what we know is that the center of the hoop, we know at all times where the center of the hoop will be. It will be at the starting point plus omega t, right? It'll just keep moving around. Relative to that center of the hoop, the bead has freedom to move around the wire, move along the wire. That's what we're quantifying with our degree of freedom, Q1. Okay, so I'm going to get rid of this red S. We're not going to use that. But now our goal is how to write down T and U, the kinetic and potential energy. And in particular, we need to be able to write down a position and a velocity. Okay. So let's focus on writing down the position. And here's the foolproof way to do it. The foolproof way to do it is to find the origin and write the Cartesian position of your object in, say, X and Y relative to that origin. Okay, so what does that look like? Well, we can draw in our coordinate system, X and Y, and then we can identify in blue the coordinates of the center of the hoop, and then from there we can move over an additional amount, labeled by green, given by the position of the bead relative to the center of the hoop. So the XY coordinates of the bead are going to be the sum of the X coordinate of the hoop plus the bead relative to the hoop, and same for Y. Okay, so we need to identify one more parameter here, which I'll call alpha. Alpha will be the angle of the line AB relative to the x-axis, and we know that alpha is going to be equal to omega t, assuming it starts with the line AB parallel to the x-axis. Okay, so the hoop is being rotated at a given angular speed omega, so that over time this angle alpha will grow linearly in time. Okay, so if we think about the position of the center of the hoop, so X center and Y center, that's this position of the center of the hoop. Okay, that we can write as the radius of the hoop, which is r, times the cosine of omega t, and r times the sine of omega t. So we can add to the center coordinates an incremental step in x and an incremental step in y that gets us from the hoop center out to our bead. And we can write that incremental step in x in the following way. It's think of a triangle with a hypotenuse r, and the base is delta x. The angle of that triangle will be alpha plus phi. Let's see that a little more closely. So I've taken this triangle and I've expanded it out over here. Radius of the circle is the hypotenuse. Delta x is the base of the triangle. And we can see that the angle down here between the hypotenuse and the base actually has two contributions, delta phi rather, and alpha. Okay. So what that tells us is that we can write delta x in terms of the hypotenuse and the cosine of that angle alpha plus phi, where alpha is omega t. And the delta y would be the height here of that triangle, which we can express as r times the sine of the angle. So once we know that, we can write the overall coordinate x of the bead as the center coordinate plus the incremental step from there. So to go from the origin to the bead, you first go to the center, and then you go from the center to the bead. That's what this is saying. So we're going to have two terms in here. I'm going to move things around a little bit. We'll get rid of that guy. We'll move this over here, shrink it down a little bit. And then let's move these over. Okay, so what we're saying now is we have expressions for x, we have expressions for y, and our goal is to write down the kinetic energy. Okay, so we're going to do kinetic energy is equal to m over 2 x dot squared plus y dot squared. But we can see that when we take x dot squared and y dot squared, everything will be in terms of phi dots and explicit time dependence. So I'm not going to do this all out, but I will just take one step, which is to look at x dot And then once you see me do x dot, I'm sure you'll be comfortable doing the y dot piece. So if we take the time derivative of this term, we'll get a minus r omega times the sine of omega t. And then for the second term, we'll have a minus r times the sine of omega t plus phi. And I left some space out front because we also have to, by the chain rule, take the derivative of what's inside. The derivative of what's inside with respect to time is omega plus phi dot. Like so. Okay, and you can do the same thing with the y term, and you're going to get like plus r omega cosine omega t, and then you'll get a plus r omega plus phi dot cosine, and then you're going to square them, and you can see you're going to get some reductions, right? You're going to get sine squareds plus cosine squareds, and then you're going to have some cross terms as well. Turns out those cross terms will not cancel, but you'll get an angle addition formula. You get like a cosine of a plus b trig identity. So it simplifies quite a bit. Okay, but the goal here is not to go and solve this problem. The main goal is to say, okay, if I have a problem that has a generalized coordinate that's not Cartesian, and also how do I write it down? How do I find an expression for kinetic energy given a generalized coordinate that's non-Cartesian, number one. And number two, wanted to make sure that we reference our system for this calculation to an inertial frame. And since we know point A in this problem is not moving, point A would be a good origin. Notice the center of the hoop would be a poor choice of origin. It would not work because the center of the hoop is accelerating. It's moving in a circle because the hoop is being driven at this rate omega. So it's not okay to treat the coordinates of the bead as just delta x and delta y relative to the center of the hoop, because you'd be doing physics in that non-inertial frame, which is problematic. Okay, so we've touched on this 5-point plan. We spent a fair amount of time talking about the first 2 points. How do you choose an inertial coordinate system? How do you know how many degrees of freedom there are? And how do you pick a useful coordinate per degree of freedom? Then we said, okay, now that we have our coordinates, what's a safe way to write down kinetic and potential energy? In other words, what's a safe way to write down position and velocity in a general problem? And we did that. And the idea there is write everything in Cartesian coordinates and then express your Cartesian coordinates in terms of the parameter of your generalized coordinate, in this case phi. The rest of this is just straight math. Very little physics at that point. So step 3 is trivial, just combine t and u with a minus sign. And then steps 4 and 5 are taking partials and taking derivatives. So it's very much turning the math crank from then on out, but a lot of the physics thinking comes in the first couple steps. So I wanted to spend time on those points. Okay, well that's it for now, but until next time, take care and be well.